This is video 2 of Unit 9, and in this video we'll talk about how to write chemical equations from scratch. The first thing we'll mention is something about the diatomic elements. Now there are 7 of them, and when these elements are alone they will double up. And the 7 are here: hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And a quick way of memorizing them is with this little acronym HONCO brief. So what happens is anytime these are by themselves, 2 atoms will link up together. So for oxygen, for example, 2 oxygen atoms will combine together. Here is the structure. We drew their structures back in chapter 6 in semester 1, but the whole point is they try to obtain an octet. By themselves, they won't have the octet. They won't be like a noble gas, so they will double up. This is really what's driving them. So anytime you see one of these in an equation, when it's by himself, you have to make sure there's a 2 at the bottom. That's what the diatomic refers to, 2 atoms when these are alone. The easiest way to memorize where they are found on the periodic table is there are 7 of them, and they form a 7 in the P block. So from nitrogen over to fluorine and down to iodine, these are all diatomic. Now 1, 2, 3, 4, 5, 6, and then they point toward the 7th one, which is hydrogen. And there you have the 7 diatomic elements. You can mark these on your periodic table as such, but these will be important to keep note of as we write our chemical equations. Next, for chemical equations, we'll introduce state symbols. These are very commonly used at the back of a compound, and they represent the state in which the substance is found. So, for example, this compound here, sodium hydrogen carbonate, is a solid. Water obviously is a liquid. Carbon dioxide is a gas. And a new one here is AQ. Now AQ means aqueous. So this actually, aqueous, which means the substance is dissolved in water. Many acids come in this way, dissolved in water. So if you have a solution, if you have yourself a test tube and the chemical is in a solution, most likely it's going to be aqueous. And aqueous means dissolved in water. So pretty simple for solids, just an S, liquids an L, gases a G, AQ if the chemical is dissolved in water. Usually we write them italicized, so as to differentiate, between the regular and the state symbols. Now above the arrow, very often we'll put some other symbols. Very commonly for a reaction to go forward, it has to be heated. So very often we'll put heat. Or we can also put a little triangle. That also means the same thing, means heat. Sometimes a specific temperature will be placed above it. In this case, 5 degrees Celsius, which means cooled actually, because room temperature is 22 degrees Celsius. Sometimes you need it 180 degrees Celsius. So these are some of the specifics that you'll see above the arrow. This is kind of the required conditions for the reaction to occur. Another very important condition is what's called a catalyst. Sometimes you'll see a compound above the arrow. If ever you see a compound, this is referring to a catalyst. Now a catalyst is a chemical that's used just to speed up the reaction. Many reactions go slowly without a catalyst. We'll throw the catalyst in there, but the very important thing about a catalyst is it itself does not get used up. So the catalyst comes right out. That's why you wouldn't put him on the product side or on the reactant side, because it never gets changed, is the idea. So a catalyst is placed above the arrow here. And what we have a picture of here is this is a catalytic converter. Catalytic converter. And this is placed at the exhaust section of a car to help catalyze all the exhaust gases coming out to make sure they're nice and clean, is the idea. A reaction, furthermore, can be exothermic or endothermic. You can hear the word thermo in here. So exothermic means the reaction releases heat. A famous example of this is whenever you burn a fire. Wood burning, which is a combustion reaction, is exothermic. That's why really we burn wood to get heat from it. A reaction can also be endothermic, which means it absorbs heat. In other words, it feels cold, and cold packs are a good example of this. Inside of here, a bunch of chemicals which, when mixed to react, become cold. That's an endothermic reaction. So think exo as exit. Very often this is the way you think of it. Exit. Heat is exiting the reaction, exiting, coming out, and you can use it. Think of endo as into. This prefix endo actually means into. Heat is actually going into the reaction. That's why it feels cold, because it's taking your heat away from you and putting it into the reaction. So these are important. Most reactions will have a heat component. Actually, if you recall, one of the indications that you have a chemical reaction is that there's an energy change. So every chemical reaction has either an exothermic or an endothermic component to it. Now, the way we write this endo and exothermic business is, for our purposes, we'll just put heat as one of the products or a reactant. So if heat is exiting, if it's exothermic, we'll put it as a product. If it were endothermic, we put it as a reactant. We put it in here. Another way of doing it, we won't be doing it this way in this class, but in AP chemistry we'll use this delta H symbol, and it's placed at the end of the reaction. And if the delta H is negative, then it's exothermic. If the delta H is positive, it's endothermic. So in this case, we would actually put delta H is negative some number. Again, this we will do more in AP Chem. Okay? So why don't we try a few examples where we write a chemical equation using all the symbols and all the rules that we've just stated above. So our equation here says zinc metal combined with aqueous hydrochloric acid produces hydrogen gas and aqueous zinc 2 chloride. So the first thing to do is to find out which word represents the arrow, so we can separate our reactants from our products. Well, the word produces is what's referring to the arrow. So anything before produces will be reactants, anything after it will be products. Now before it, we have zinc, metal, and we have hydrochloric acid. So those are going to be our two reactants. Now reactants are separated with a plus, just to show that we have two different substances. So we have zinc for the first one, and we have HCl for the second one, hydrochloric acid. And then after the products, we have hydrogen, and we have zinc 2 chloride. So hydrogen. Now hydrogen, one by itself, is one of those diatomics. So we will have to put a 2 down below. And then zinc 2 chloride is written as ZnCl2. It's important to include that 2. Remember, this 2 means zinc has a +2 charge. Chlorine has a -1 charge from the periodic table. We need 2 chlorines for every 1 zinc. Make sure you write it in this way. Okay, furthermore, we will have to write in the state symbols. So let's go ahead and do that. And usually you take a look at the reaction and see for any clues about what the state could be of the substance. Now here it says it's a metal. So zinc, metals are solid, so you can put a solid in there. And hydrochloric acid is said to be aqueous. That means it's dissolved in water. All acids you'll see will be aqueous. So we'll put AQ at the back. Next, we will have hydrogen. Now we know that hydrogen is a gas. It's also pointed that out in the equation itself. So we'll put a G here. And finally, zinc 2 chloride is also aqueous. So we'll put AQ at the end. Lastly, we have to make sure we balance the equation. From now on, it's a good idea to make sure any equations that you write are balanced. So let's go ahead and see how we should balance this one. We have 2 hydrogens on the right. We need 2 on the left. We'll put a 2 in front. That gives us 2 chlorines. 2 chlorines. We have 1 zinc. 1 zinc. We are good. So this is how you would write the reaction of zinc metal combined with aqueous hydrochloric acid to produce hydrogen gas and aqueous zinc chloride. Let's go ahead and try one more. Actually, go ahead and do this next one on your own. Pause the video, try this one. And why don't we try this last one together, example 6. So we're told that copper solid copper 2 carbonate decomposes into solid copper 2 oxide and carbon dioxide gas upon heating. So let's think about which word here represents the arrow, which word separates the reactants from the products. And if you think hard, you'll see that decomposes is the word that separates the two. So decomposes will mean the arrow. On the reactants, we have only one reactant, solid copper 2 carbonate. On the product, we have copper 2 oxide and carbon dioxide gas. So only one product, copper 2 carbonate. The way to write copper 2 carbonate is CuCO3. So you have to consider these polyatomic ions. Copper has a +2 charge, carbonate has a -2 charge, so you'll only need one of each. Solid copper 2 oxide, the way we write copper 2 oxide is CuO, again because copper is a +2, oxygen is a -2, you only need one of each. Here's how we write copper 2 oxide. And carbon dioxide gas. That one's pretty easy, covalent compound. Next, let's put in the state symbols. And we're told that copper carbonate is a solid, so put a solid in there. We're also told that copper 2 oxide is a solid, makes it easy. We know carbon dioxide is a gas. Lastly, make sure it's balanced. And before actually we balance it, it says upon heating, we have to heat this thing. So we'll actually put heat above the arrow. I'm going to put heat. Heat is required for this to happen. If you just put copper carbonate by itself, it will not decompose. You have to put heat into the system. That's why we put heat above the arrow. And the equation is balanced. If you take a look, we have a copper on the left, copper on the right, 3 oxygens on the left, 1, 2, 3 on the right, 1 carbon, we are balanced. So there you go. Go ahead and try the last one on your own, and we'll practice a lot of this in class.